Thank you, Michel. Yes, so I did indeed want to talk in this presentation about my new COBIA-based CAPE-OPEN unit operation, which is the Python unit operation. Good afternoon, good morning, good evening, everybody. So why Python? Let's start with a bit of motivation. If you Google the most popular programming language, Python will currently come up as #1. Python has made a remarkable climb to be the most popular programming language in the last couple of years. So to understand why this is, I made a list of pros and cons. The first con is Python is slow, but this is only a minor con, because if you look at the pro side, most code executed from Python isn't actually Python code. If you would, for example, use an optimizer in Python, it is most likely from the SciPy family, which is implemented in highly optimized native C++ typically, or C. The next con is Python is ugly. There's probably a reason they named the language after Monty Python, because it's so ugly it's almost funny. Personally, if there's spaces and tabs that make part of the syntax, I get all nostalgic. I think we're back in 1977. But on the plus side, Python is, for most people, rather easy to understand and an easy language to learn, so that's good, of course. My biggest problem with Python is it does not happily do multi-threading in a production environment. I will expand on that a little bit more later. But there is a large ecosystem of support libraries available for Python, and those two pros, of course, make that Python is really popular. It's easy to learn, and you can get started with a bunch of pre-programmed objects that you can easily access. So also in our CAPE-OPEN community, there's a large drive for Python. After the 2020 annual meeting, there was a questionnaire. And from that questionnaire, it became clear that people really want to have a Python COBIA binding. I hope that the Python CAPE-OPEN unit operation and its sister product, the Python CAPE-OPEN thermo import, can kind of fill this gap to some extent, but the Python unit operation is not a COBIA language binding. The difference is that in a COBIA language binding, you would expect to implement CAPE-OPEN interfaces in Python. So yes, the Python unit operation is actually built on COBIA, but no, you do not implement CAPE-OPEN interfaces in Python. What you do is you use a specific Python unit operation API to program your unit operation. So now that we've had a bit of motivation during this presentation, I would like to present what the Python unit operation is. And during implementing it, I actually learned a lot of stuff that could be used in potential COBIA Python language binding, which I will also share with you in this presentation. So the Python unit operation isn't actually one unit operation. If you ask the Python unit operation class factory to create a Python unit operation, it will first check which Python you have installed on your system, and it will select one of the Pythons that's supported for the proper bitness. That is to say, if you run a 64-bit PME, you need a 64-bit Python. If you run a 32-bit PME, you need a 32-bit Python. So it will instantiate the actual unit operation DLL of the proper bitness and the proper Python flavor. All of those unit operations actually share the same editor, and that editor component in turn builds on the Scintilla component, which allows us to have nice syntax highlighted Python editing in a unit operation. And for those of you that are not familiar with Scintilla, this is the editing component that underlies Notepad++, which is rather popular on the Windows platform. So I'm going to run you through the Python unit operation just by looking at the example that you get when you just drop a Python unit operation in the flowsheet. The example that you will get is a simple heater where the amount of heat that you add to your feed stream, between your feed and your product stream, is given by an input parameter. And if you double-click the unit, this GUI will show up, and there's two functions here of interest. You will need to provide a configure function, and you will need to provide a calculate function. There's more functions that you can provide, but these are the two that are required. The rest is all optional. So in the configure function, as the name suggests, you are configuring the unit operation. So you can add ports, and you can add parameters, and you can add two kinds of reports. You can add textual reports that were already supported by CAPE-OPEN 1.0 and 1.1 unit operations. There's also in CAPE-OPEN 1.2, as this is done via COBIA, the ability to make image reports. So if you're using the Python unit operation from a a COBIA, from a COBIA-based PME, you will be able to access those via the CAPE-OPEN reporting interface, which is new in CAPE-OPEN 1.2. If you're using COBIA to run this Python unit operation in a 1.0 or 1.1 unit operation, then you will not have access to these images via the reporting interface, but you can still inspect them in the reports tab there. So as said, this is not implementing a CAPE-OPEN unit operation. You don't actually have to program your own port collection. You don't even have to program your own port object. What you just do is you tell the unit operation, which is passed as an argument into the configure function, that you want to add a port, and you can immediately see the result on the ports page. So you add your feed, you add your product, you say that they're of the material port type, and one is a feed, the other one is a product. The Python unit operation supports material ports, energy ports, and information ports, so you have to specify which one it is. Then, of course, you can also add parameters. Again, you don't have to write your own parameter object or your parameter collection. You can just say add a parameter. You specify its name, its mode, which is input or output, and its data type. And optionally, you specify a unit of measure or a dimensionality. So the Python unit operation does support real, integer, Boolean, string, and real array parameters. All of those you can just create just by adding a parameter in the configure function. So similarly, you can very simple add a report, which is not shown here. That can be an image report or a text report. Let's focus on the calculate routine now. The calculate routine shown here is again the very simple example of a heater for which the heat duty is specified. So what I've outlined here is for the feed port all the functions that you can access directly. If this is not enough, the entire API that is also exposed by the Python CAPE-OPEN thermo import module is also available on all objects that are connected to material ports. So again, you're not implementing CAPE-OPEN interfaces here. For example, if you do a calculation on a feed product, which we do here, we calculate enthalpy, you're supposed to make a duplicate of the connected material because your calculation cannot have a side effect on the feed stream. This is all done under the hood for you, so you don't have to worry about that. Then the CAPE-OPEN unit operation standard specification requires that you flash the product port, like the feed port, the product port available from the unit.port dictionary. The flash in this case is executed by the set function. This particular unit is executing a pH flash where the pressure is taken from the feed port and the enthalpy is calculated by adding the heat duty parameter value. The parameter itself is available from the unit.parameters dictionary. The value you can get for input parameters and set for output parameters. The parameter object has some more members. It has a name, it has a description, it has an isInput member, and it has a data type. These are read-only during execution time. And raising errors is actually as simply as raising a Python runtime error. What you see here is the response of coffee. If you right-click a unit and you say calculate unit and the runtime error is generated, this will translate into a CAPE-OPEN error, and the simulation environment will make whatever went on clear to the user as it sees fit. So that was a really simple example, of course. Fortunately, we have created a lot more examples. If you go to the AmsterCHEM website, you will find a whole stack of examples, each of which have a walkthrough and the code to execute this unit operation from the Python unit operation. If you really want to get right into the complicated matters, then perhaps the best example to start is example number 12, which is a multi-stream shell and tube heat exchanger. This uses SciPy for the solvers. It solves the temperature profiles along the heat exchanger. It uses persistence validation. It actually plots the temperature profiles along the reactor and delivers that as image reports. So have a look at the AmsterCHEM website. All the examples are there. So that was the introduction to the Python unit operation. I promised that I would share some learnings for what I learned when writing this Python unit operation, what we can use in the context of a COBIA Python language binding. And I also promised that I would elaborate on why Python is not the most suitable environment for multi-threaded production software. So the first question is, who brings Python? What Python is brought to the table? On my computer, I actually have a whole nest of Pythons. They seem to multiply. The other items that I want to discuss is multi-threading and the issue of lingering references. So there goes. CAPE-OPEN is all about interoperability. So we have a PME and we have multiple PMCs. All of those could be by different software vendors. So all of those could potentially be using Python. Of course, if the PME is using Python, it has already started Python for you. The PMCs might be expecting a different Python, or maybe it's up to COBIA to load the Python, but then you have to identify which Python is required. So the thing about Python is, unless you want to compile your own Python, it comes in a DLL. All Python 3 family DLLs are called Python 3.dll. The Python unit operation actually does not load that thing because that would immediately lead to conflicts. It will load the version-specific DLL, which is Python 3.8.dll or Python 3.9.dll. And it will link statically to that because dynamic linking requires finding all the Python functions in that DLL and loading them, which is a bit over the top. Does the PME bring Python? If the PME brings Python, is it the version of Python you were expecting? If not, how do you respond to that? Should COBIA load Python? The Python unit operation actually has fairly complicated machinery to deal with all of this. It can deal with the preloaded Python. It can deal with the Python that you specify yourself where it lives, as long as if it is a supported version of Python. So for the COBIA Python binding, clearly we need some design here on which Python is to be used. Multi-threading is a bit more of a complicated issue when it comes to Python. The Python interpreter, alas, is not thread safe. Therefore, every access that you make to the Python interpreter itself, you must shield by the global interpreter lock, or the infamous GIL. This means that if you want to execute some Python code, you first need to put a lock on this GIL. Then the Python interpreter might internally unlock the GIL for a bit to do some lengthy work that is not interpreter related. Then the Python interpreter will immediately acquire the lock after that, and once you return, you need to unacquire the lock. You can imagine that having to lock access to the Python interpreter is kind of detrimental to multi-threading performing. There is actually no multi-threading effectively when you're using Python. So this is interestingly also how the Python threading module works. If you look at the Python specification, this is taken from the 3.10 specification, it will tell you that the global interpreter lock will prevent actual multi-threading to occur when Python is executing. So it offers a way out via multiprocessing, but in multiprocessing we'll get marshalling, which is also costly. That's probably not the best option. Another option is the use of independent sub-interpreters, and the Python API actually offers functionality to make sub-interpreters. But if we read the Python enhancement proposal for this particular sub-interpreters, or even if we read the API specification, there are some really scary things there. So this is from the API specification. It will tell you that if you are using sub-interpreters, you stand very well the chance that extensions such as C-types will break. And C-types, of course, is something that we're definitely going to need for native interop. Also keep in mind that we are sharing perhaps Python with other software components within the process. So if we're using Python with sub-interpreters in one part of the process, there's no guarantee at all that we won't break another part of our process. Just not ideal. The Python enhancement proposal actually makes a disclaimer about the GIL. It says even if you're using sub-interpreters, you're not actually avoiding the GIL at all. So stripe that. Let's not use sub-interpreters. So that is to say that we need more research on multi-threading before we make a proper Python COBIA language binding. There is currently actually a lot of research going on in Python, making Python internally thread safe and therefore allowing multiple threads to execute Python code at the same time. But as far as I'm aware, none of this is publicly available, at least not in a mainstream release. It might be in a few years, so this problem might resolve itself, but maybe we don't want to wait a few years. Finally, there is the issue of lingering references. Okay, so to understand lingering references, we have to also understand that CAPE-OPEN defines very well the lifespan of a number of CAPE-OPEN objects. For example, when a PMC's terminate function is being called, a CAPE-OPEN requirement is that all external references are terminated. You need to drop all external references. Also, if you do a calculate in the unit operation, you may need to duplicate the material object that is connected to a feed to do a property calculation on the feed. and you must drop any reference to this particular material object prior to leaving calculate. The lingering references problem makes that you cannot always drop these references because they're lingering. This problem is not unique to Python. Many garbage collected languages such as .NET and Java suffer the same issues because the object that implements the reference isn't actually really cleaned up until garbage collection time. Many .NET unit operations work around that by explicitly asking the marshaller to release an object if it's a COM object, but that's also fraught with danger because if you're releasing an object, the entire object is released. You're not actually necessarily sure whether that object is implementing just the interface that you asked for or also another interface. For example, a parameter in CAPE-OPEN 1.0 is the parameter interface, but you can also ask it for a different object, which is the parameter specification. And it is inviting to drop all references to the Python specification object once you're done with it. But if it actually is implemented by the parameter itself, you're also killing off the parameter there, which is going to lead to fairly unpleasant results, namely that the parameter isn't accessible anymore. So the lingering references issue in Python isn't actually resulting from garbage collection. It comes from a rather unexpected corner. If you raise an error in Python, Python internally makes 3 global variables. There are last type, last value, and last traceback. Last traceback, that's a pain because it contains all the stack frames that were on the call stack when the error was raised, and all the variables that were on the current stack, all the local variables, also retain a copy in there, which might very well involve CAPE-OPEN based variables, and therefore a reference will be held to those objects until the last traceback is deleted, which you can do explicitly, of course, but these are global variables, and again, we might be sharing Python with other software components in the simulator, so manipulating these global objects is not ideal. So that was it for my learnings. Some concluding remarks. The Python unit operation is available from the AmsterCHEM website, as is the Python CAPE-OPEN thermo import. You can try them both. They're free for academic use. You can give it a test spin. The Python unit operation comes with a 1-month trial license if you install it. And for COBIA, if we move forward with the COBIA Python binding, then we should carefully look at the design there when it comes to threading and when it comes to who brings Python to the table. Thank you for your attention.